Alright, now we're looking at the next section here of chapter 3. So, first thing we're going to talk about is the regression line. So, a linear relationship between two quantitative variables are common and easy to understand. A regression line summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict. So there's an example here from the textbook. So they have this regression line here. The explanatory variable is non-exercise activity. The response is fat gain. And so they just start interpreting the scatter plot here. So the regression line here is predicting the fat gain based on the change in non-exercise activity. Alright, the regression line is just a model for the data. So it gives us a mathematical description of what's happening. So just remember some of this notation here. So this y hat was our predicted value, a is the intercept, and b is the slope. And so remember, sometimes you're asked to interpret those values. So here's that same example there. So the slope tells us how much the amount of fat is going to change for each added calorie of non-exercise activity. And this is the estimated starting fat amount if the person does not, if their non-exercise activity is at 0. Then we can use the line to make predictions. So you can plug in, if you wanted to predict the fat gain for 400 calories, you would just plug in the 400 there and you can make that prediction. Alright, so just remember that concept of extrapolation. So the line is really, when you're extrapolating, if you're trying to make a prediction outside your observed values of x. So just don't make a prediction using values of x that are much larger or much smaller than those that actually appear in your data. So if I go back to this example right here, it wouldn't make sense for me to make a prediction for 2,000 calories because it's way outside my data. I would be extrapolating and it just wouldn't be an accurate prediction. Alright, we also discuss residuals. So in most cases, no line will pass exactly through all points in a scatter plot. So a good regression line is trying to make those vertical distances as small as possible. So remember, your regression line is the your residual is the observed minus the predicted. So the good regression line is trying to make those distances there as small as possible. Alright, we talked about the least square regression line in class. So you could have other types of regression lines, but the least square regression line is the type we use. It's just regressing the line, so the response variable on x. And it's taking those residuals, it's squaring it, and it's trying to make these squares as small as possible. Alright, so we can use technology to find that least square regression line, which we did, and I'll show you shortly. But remember, there's this shortcut method right here, and these formulas are on the formula sheet, so you don't want to forget that. This shortcut method was that you could find the slope if you had the correlation coefficient, so the r, and you had the standard deviation of the y's and the standard deviation of the x's. And then you could find the intercept if you had the average of the y's, the slope that you just calculated, and the average of the x's. So it was just a shortcut method, so don't forget that. Alright, we also looked at a residual plot. And when we do a residual plot, we're looking for a random scatter. And I'll show you how to make one of those again on the calculator. But the residual plot, you just had the x variable, so the explanatory variable plotted against the residuals. And as long as that is randomly scattered, we could say that the linear model is a good fit for this data. So again, we're looking for no obvious patterns. So in this one right here, this example, this is the original data. There's the x. This is the x and this is the residual. So there's a curved pattern here. So the residuals are showing a pattern which would make it suggest that a linear model is not appropriate. When I look at the original data, so there's the x's and the y's, you can see that a linear model is not appropriate because it is still curved. So you're just looking, remember that residual plot is supposed to have no pattern. We also had something called the standard deviation of the residuals. So we found that by doing, you can take these, you can square the residuals, add them all up, and then divide it by n minus 2 and take the square root. I also showed you how to find it in the calculator, so I'll show you that again. Last thing we had in this section was talking about the r squared, which is the coefficient of determination. Don't forget that term there. It's the fraction of the variation in the values of y that is accounted for the least square regression line of y and x. So you can calculate r squared using this formula right here. I also just showed you how to find it on the calculator, so I'll show you that shortly. So this is back to that body weight and pack weight data that we had from the first video. And what I'm going to do here, so first thing, after I ran that linear regression, you can see that that r squared is right there. Remember, it's just really the square of the r. So it says it's 0.6315. Let me see when I go back here. So it was 0.6315. Alright, so then 0.6315, when you do, this is how much is, there it is. So 0.6315. So then the r squared, so if you actually went through and found it all by hand, which I told you not to worry about doing, so what that means, so here's the r squared here, they did it by hand. It's 63.2% of the variation in backpack weight. So it's the variation in the y variable is accounted for by the linear model relating pack weight to body weight. So we always said in class like 63.2% of the variation in backpack weight is explained by the regression on body weight. So then you can say that 36.8% is unaccounted for or unexplained. So other things that would be explaining it might be just how long you're hiking for, or you know, how much food you're going to need, or things like that. So there's other things that explain why this isn't a perfect fit. So you also remember when you run this linear regression, so this is that backpack weight. So there's my intercept, there's my slope, so you can get that from there. When I do that equation here, so if I do that, if I go back to that stat again, I go to calc, and I go down to option 8. If I do L1, comma, L2, comma, vars, and then I go over to those y vars, function, I press enter, and I press enter again. It adds that y1 there, and if you remember what that does for me is it stores my equation in my y equals, and so then what I can do if I want to make a prediction, let's say I wanted to predict the backpack weight for, let's see, let's look at this data again. For a 120-pound body weight. So what I could do here is I can just type in 120 and it'll make the prediction for me. So if you just remember that. To find that standard deviation in the residuals, what I had you guys do is I had you go to the test, and then you can either do F or G, it doesn't really matter. I'll just choose F. Okay, oops, I'm not doing the right thing. Alright, so then the x is in list 1, the y list is in list 2. Don't worry about this, don't worry about putting the equation in. And just hit calculate. And when you scroll down, there's that S right there. So the standard deviation of the residuals for this data is 2.695. So it's almost 2.27. So that just means my predictions for that pack weight may be off on average by 2.267 kilograms or whatever it was. Another thing that you do, let me show you the residual plot again too. Remember when you run that regression, the calculator always creates that list for you, that resid list. It may not be number 7 on your calculator, but it'll always be created after you run the regression. It's only done after you run the regression. So I can create a scatter plot, and I'm still going to use my x's, but I'm not going to use that y list anymore. I'm going to graph it against the residuals. So I'm going to go to second stat because it brings up my list. I'm going to use that number 7. I'm going to hit zoom 9, and there's my residuals. So I'm going to there's not a lot of points here, but there's 3 here below, there's 4 here, there's 4, so there's 4 above, 4 below, so I'm just going to say that this is uniformly scattered and a linear model is appropriate. We did see that the R wasn't very high with this data, so the linear model is maybe not perfect, but at this point we'll just say it's okay. So back here, just another thing to remember, they might give you some computer output, especially for these kind of problems. So remember this first line here always relates to the intercept. This second line always relates to the slope. So the coefficient column, this is actually your intercept. This is actually your slope. This is the standard deviation of the residuals. This is the R squared. So oftentimes they give you that. Here's another output, again with the same type of information. So just some things here to remember about, so correlation, if you're doing regression, you need to distinguish between explanatory and response. If you're doing correlation, it doesn't matter. If you're just trying to find the R, it doesn't matter if you switch those two. If you're trying to make an equation for the line, it matters which one is which. And here's how they're showing you how they're different based on if they switch everything. Correlation and regression are only good for linear relationships. So if a relationship are not linear, then you don't use correlation and regression. Correlation and least square regression lines are not resistant. So when there's these outliers here, things can really throw things off. So here's an example of just some data where if you take out some of these children, like child 19, child 18, it just changes the regression line. Again, they only describe linear relationships and they're not resistant. And then there were some things there that we discussed about outliers and influential observations. Just because two things are correlated doesn't mean that one causes the other. We can only say that something causes the other if there's actually been a controlled experiment done. And here's the summary if you want to read through that.